Hey guys, welcome to this session on rational and irrational numbers. I'm actually doing this lesson from my house because there's about 11 inches of snow on the ground and we got an e-learning day today. So to help you out with rational and irrational numbers, and specifically irrational numbers today, because we've already talked about rational numbers in class, I wanted to record a quick video for you. So with that said, quick recap. We've talked about rationals, like I said, but I wanted to kind of give you this this visual. It's similar to a lot of visuals that you'll see if you look up rational and irrational numbers online. And keep in mind that a lot of this stuff is applying to the level of math that we're at. Now, it gets a little bit more complicated, but these are the numbers that we're going to talk about in 8th grade math today. So all real numbers are made up of either rational or irrational numbers. And you can see there's a lot more categorization to the rational side than the irrational side, which is kind of one group of irrational numbers. So if you want to think about this, okay, we talked in class about if we had a certain kind of car, like in my car, I have a black Subaru Crosstrek, okay, or in my garage, I have a black Subaru Crosstrek. Well, my Crosstrek is the most specific kind of vehicle. So that would be the center. It would be kind of like this part of that visual if I did this for my car. Okay, but more specifically, it's a Subaru. Or sorry, more broadly, it's the Subaru. Okay, so a Crosstrek is a Subaru, and a Subaru is it's a type of, like you could say, maybe it's like a sedan. Okay, so there's lots of different sedans, and then you could have sedans within the category of vehicles, and you just get broader and broader as we're going out. So think of this as being very specific in the middle and being more broad as we go out. So you can say like, oh, a strawberry is a kind of fruit, and a fruit is a kind of food group, and a food group is a part of food, and whatever, something you consume, so you keep getting more and more broad. I also thought of a good way to explain it to my students is like, think about it this way. If you were like a little toddler and you're sitting at dinner with your mom and dad, and they're like, you ate your veggies, good job. You're going to get some cookies tonight for dessert. So let's start counting your cookies. Well, you would start counting very naturally, natural numbers, 1 cookie, 2 cookies, 3 cookies, right? And then the next night, maybe they said, you had a lot of cookies last night. You don't get any more cookies tonight. So that's going to be including whole numbers, which is 0. You're just adding 0 to the mix right there. So you sort of had this your understanding of numbers as a toddler might broaden to like, ooh, I understand 0. That's not good. I want more cookies. And then maybe you have like a sister or a big brother or somebody who takes your cookies. And so then you're starting to include things like negatives. Now we're not doing anything with decimals or fractions yet. Integers just are including negatives into the mix. So you could have positives or negatives. 1, 4, -7, -33, 45, 1,000, doesn't matter. It could be a huge number or a really, really small number, but no decimals or fractions. So then once we get to rationals, the broadest category to include everything is going to have fractions, decimals, positives, negatives, and even repeating fractions and repeating decimals as well. So as long as there's a pattern to it, if it's repeating, it's allowed to be irrational. Okay. Then over the irrational, we cannot have anything that is repeating, or it can't be repeated. It's got to go on forever. So this is how I kind of organize it. It goes on forever and it has no pattern. Okay, so that's irrational. Think of it like a crazy old aunt on the phone who's talking and talking about all sorts of weird stuff, and you're just like, oh my gosh, when is this phone call going to end? Because she's going on forever and she's not making any sense. There's no pattern here. So that's irrational. Okay, your 2 things that you want to look for are pi. Again, this is at our level of math. We're looking for pi, and we're looking for non-perfect square roots. You could also look for non-perfect cube roots, but we're not required to know that in 8th grade in the state of Indiana, so I'm not spending a lot of time on that. So look for non-perfect square roots and pi. Those are our big look fors. If you can find those, that's going to make your life a lot easier when you're just trying to hunt down those irrationals. So I went ahead and put a non-perfect cube root as an example here. This has a pi in it. This has a pi in it. Anything where you see pi, unless it's like pi divided by pi, which would be 1, but mostly we're going to see things that have to do with pi as being irrationals. Okay. And 2 and 3, those are non-perfect squares. So they're not going to have a perfect square root. So they're going to be some sort, if you plug that into your calculator, it's going to be a decimal that goes on and on forever with no pattern. So if I ask you to classify some numbers, okay, 0 0 is not, you don't count 0 cookies right at first, right? But you do when you start to count whole numbers. So 0 is a whole number. It's also an integer and irrational. It can belong to all those. It's part of those broader categories. 14 pi, well, anything to do with pi, remember, is irrational. Because if it's crazy and goes on forever with no pattern, and then we just multiply that by 14, that's just 14 times the craziness. Right here, we have negative 121. Okay, it's allowed to be a negative outside our radical sign. 121 is a perfect square. If you weren't sure, you've got to know those perfect squares. 121 is the square of 11. So the square root of 121 is 11. So this would be negative 11. Now, negative 11, I wouldn't start counting negative 11 cookies as a toddler, right? And it's not 0. It's an integer, okay? So you want to make sure that you are including that as an integer. This one right here, 64 divided by 16, is going to be the number 4. It's a nice, neat whole number, right? So that's rational. It's an integer. It's a whole number. It's natural. It's all 4 of those, right? It could, because it belongs in this category of rational. So it's also whole, an integer, and rational. Last but not least on this page, the square root of 14. If you plug that into a calculator, it would go on and on forever with no pattern, except your calculator stops, but the number doesn't. So if your calculator's like, I can't do this anymore, I have to end somewhere because I'm a physical calculator. Okay, that's because it would technically go on forever and ever. And we've talked about this in class. No one wants to spend the rest of their life writing a number, right? And then even if you died writing that number, then it would still not be done, and that would be a pretty boring way to live your life. So rational and irrational numbers, that's how we categorize things. So to make sense of things in the world, we have to know how to categorize them, how they compare to other things. So another way of thinking about this is they're going to ask you to approximate certain sorts of square roots. So you know any old traditional number line. This one I just did 0 through 8 really quickly, just scribbled it down. Okay, so if I want to rename those numbers, because we talk about how numbers have nicknames all the time in math, if I want to rename them, I know that 0 is the square root of 0, 1 is the square root of 1, 2 is the square root of 4, right? Square root of 4, plug that in a calculator, you would get 2. The square root of 9 is 3. So these are the same numbers, the same value, but not the same name. Okay, again, I'm Mrs. Landers. My mom calls me Jilly Bean. Okay, I'm the same person, I don't change, but people refer to me in a different way. So you could just finish this out here and make that the square root of 16, the square root of 25, the square root of 36, square root of 49. And again, go on for a pretty long time, but we have other things to do with our time. So they're going to ask you, all right, smarty pants, you know so much, approximate the square root of 52. So what I have to do is I had to put things in terms of those square roots and say, okay, well, if I'm looking at the square root of 52, I'm going to look at which 2 square roots it's between. And I usually think in terms of perfect squares. 52 is between 49 and 64. It's a little bit closer to the 49. So it's going to be, its square root is going to be a little bit closer to 7. Makes sense, right? So 52, the square root of 52 is right there, okay? Probably somewhere right here, maybe like 7.3. I don't know off the top of my head. And my phone is being used to record this video, so I don't have a calculator on hand. So probably like 7.2 or something like that, okay? But you can always use a calculator to confirm that. Negative, don't let negatives throw you off, okay? Now this negative is not on my specific number line, but I know that that's between the perfect square root of 100 and 121, okay? And I can think of it as negatives. So that's going to be closer to 100 than it is to 121, a little bit closer to that. So this is negative 10, this is negative 11. I know its square root is going to be a little bit closer to negative 10. So it's probably going to be something like negative 10.4 or something like that. Okay, again, you can always check that with your calculator. And then the 27 divided by 4 is 6 3/4 or 6.75. Okay, so don't let that throw you off. You might have to find out what that answer is underneath your radical sign. 6.75 is pretty close to 4 and 9, kind of pretty close to the middle. So its square root is going to be pretty close to the middle of 2 and 3, probably like probably 2.6 or so, maybe 2.5, 2.6. Okay. So making sense of those numbers and understanding what you're doing is you're just getting their nicknames. Okay. Comparing the nicknames and then go back to that square root format is going to give you the answers. The last kind of question you're going to have on this sort of, or on this lesson, so many beautiful notes written here, right? Is they're going to say, hey, tell me the distance. Ooh, sorry about that. Tell me the distance between 2 points on a number, like a coordinate grid or something like that. Okay. And you could think of this as like if you were looking at a map in real life and you want to know the distance between 2 places, so you quickly figure that out. You actually could. Okay. So, and not with Google necessarily. So the best way to do it when we're doing a problem like this is jot a picture down. Now you don't actually need the picture, but I want to show you for this sake. Okay. So one point is 1, 2. So I go over 1, up 2. That's approximately 1, 2. And then 7, 6. I'm going to go over 7. So 1, 2, 3, 4, 5, 6, 7. It's important to make your dashes about the same distance apart. You don't have skinny distances and wide distances. So that's over 7, up 6. So 1, 2, 3, 4, 5, 6. So about right there. And they're saying, hey, what is this mystery distance between those 2 points? You might be like, I don't know this. I just drew this. It's just some random thing here. Well, what you can do is you have the power to make a triangle out of that when you're on the coordinate plane. So if you do that, you can make this distance and this distance. And again, you might be like, I don't know what those are. It's hard because my drawing is sloppy and my handwriting is bad, but you do know the distance because you know that you went over 1 right here and over 7 right here. So what's the space between 1 and 7? That's a distance of 6. And you could also count the distance 1, 2, 3, 4, 5, 6. Okay. And then the distance up and down was up. We went up 2 on the first dot and then up 6 on the second. So the space between 2 and 6 is 4. This should sound familiar because of our work with slope. And we have 6 and 4. Those are the legs of a perfect square. And we already learned Pythagorean theorem, which is a squared plus b squared equals c squared. And this long side across from that perfect corner is our c, always our c. So that's what we don't know. A could be, it doesn't matter, 4 or 6. So let's do 4 squared plus 6 squared equals c squared. 4 squared is 16. 6 squared is 36. That is 52. And 52 is not our answer, right? We can't just say c squared equals 52, so c equals 52. No, you wish, but you can't. You have to find the square root of both sides to cancel out that square. So squaring and square root are opposites. Now we get plain old happy, simple little c, and the square root of 52 is going to be a little bit over 7, probably about 7.2, because I know that 49, the square root of 49 that's okay. So that's the last kind of problem that I wanted to show you. Just a quick reminder, once again, irrational numbers, look for anything that's a non-perfect square root or cube root, and then pi, and then that's because they go on forever with no pattern. Don't be afraid to rename your numbers, give them nicknames, compare the nicknames, and then go back to their square root format. Real numbers include irrationals and rationals. Think about that little toddler counting the cookies. Then we add 0 to the mix. Then we add negative numbers to the mix. Then we throw in decimals and fractions. Okay. So rationals include all of those things within. You need to be able to classify those and then apply the Pythagorean theorem on a couple of those problems when you have to find that missing distance on a coordinate plane. That's it. Enjoy your snowy day. Bye, guys.